Okay. Let's start. So it is a pleasure to have here today Giovanni Fantuzzi. I met Giovanni when we were both PhD students. We were doing research at the Woods Hole Oceanographic Institute at that point, and we were both doing computations, and we were both doing fluids, and we started talking, and we haven't stopped talking since then. So Giovanni he's one of those cases where he is from Imperial College for real, undergrad, masters, PhD, and postdocs at Imperial, and well, also some stints at Oxford, etc. And nowadays he is a junior professor at the Department of Mathematics in FAU in Erlangen in Germany. Giovanni is an expert in fluids, in polynomial optimization, and maybe has gotten into this data-driven polynomial optimization. He's going to be talking about this today, so let's give him a round of applause.
Yeah, thanks. It's a pleasure to be here. I'm really excited about being down in this part of the world for the first time. It's been great. And so, yeah, it's a pleasure here to talk about this work that combines a few things that I've been doing. But I should start by saying that this is joint work with my colleague, Jason Bramberger from Concordia University in Canada. He's really the data-driven guy in the talk. So I put a little bit of the polynomial optimization stuff, but many of the ideas came from him. And when we got together, we started talking and we realized that we have a lot of technology to analyze dynamics if we know you covered an equation, if we have models. But on the other hand, we also have a stronger drive to do data-driven analysis, right? We have explosion of data. And so we wondered, well, all the techniques that we have on the model-based side of analysis, do they just go out of the window? Or can we somehow do something similar in a data-driven setting? And so the point of the talk would be to try and convince you that maybe there is a path towards not reinventing the wheel, but reusing technology that we know works really well if we have models for these dynamical systems. And so that's kind of the point of the talk. Right, so I talk about system analysis. What do I mean by that? Oh, by the way, I should say, if there are questions, feel free to stop me anytime. And if you're following on Zoom, please just unmute yourself and give us a shout because we can't see you. So yeah, that's it. So what do I mean by system analysis? What kind of questions I'm interested in? Well, for this talk, I will focus on three particular ones. The first one is stability. So suppose you have a dynamical system like a drone that's hovering and is perturbed. Well, you would like to make sure that no matter how you perturb it, then it goes back to its stable equilibrium position, which will be the stable hovering position in this case, right? And of course, you could test, like it's happening in this example, but you can't test all possible perturbation. You would like mathematical proofs that the system is stable. Another type of question that I'm particularly interested in is, suppose you have a dynamical system, maybe complicated. You will see here a reasonably simple one, but it's still complicated enough. And you want to know how it behaves in the long term, right? Maybe you don't care about the detail of this system, the detail of evolution, but you care about what's going to happen on average if the system evolves over a long time. So I talk about averages over, let's say, long or infinite time. And what you will see here is a simulation of a three-dimensional ODE, so rather simple system, but that describes the position of this point in space. And you will see that the evolution is chaotic. And what I care about is what is the average vertical position of this point. And what you will see here on these two plots on the right is a measurement of this vertical position on different scales, 0 to 60 and 0 to 2, to give you a zoom in near 0. And we record both the instantaneous position and the average. So if I let the simulation run, you will see that the point starts to move around, and then every now and then it sort of shoots up. And what you see is these intermittent bursts in the Z3 coordinate. And if you zoom in, you see that the blue line here is the instantaneous value. The red line is the average. And if you care about the average behavior, you see you have to simulate for a very long time to get a steady converged average value. The average value is indicated here at the top of the plot. You see it's about 1, but it keeps oscillating. And even for such a simple system where we can basically run simulations very fast, we need to run a very long simulation to get a very good average. And in fact, we can never simulate for infinite time. So what do we do? Right? So this is the sort of question that I want to answer. And then a little bit more, suppose that you have these chaotic dynamics, can we somehow go from chaos to order? And so the idea here is to somehow view a chaotic attractor, let's say this Rosler attractor that you have here on the left, and view it as being a combination of simple solutions of your dynamical system, simple trajectories, which are periodic. So here on the top left, you have a single loop where a particle sort of goes around once, shoots up a little bit, and then goes back to its starting point, right? So if you imagine starting from roughly here and then going around once. But then maybe you have another one where you start from here, you go around once, you then shoots up, and then you go around another time. So you have to circle around the x1, x2 plane twice before you go back. And then you can find other more complicated orbits, which go around 3 times, maybe there's 2 of them, one that goes around 4 times, and then there's gonna be a number that go around 5 times, 6 times, 7 times, and so on. Right, so you could imagine as these being the building blocks, where if you take a combination of these, you get exactly the chaotic picture on the left. So there's theory that allows you to do this. The problem is that in order to apply this theory, you need to know these building blocks. And these building blocks are normally unstable, meaning that if you run a simulation, you don't see them. If you run a simulation, you see the picture on the left. So how do you find the guys on the right? Right, there's of course good techniques to do that. And I will somehow hope the last example in the talk would be to show you that we can extract some of these things from data using these techniques from polynomial optimization. Right, so these are the 3 questions that I want to focus on. The outline of the talk will be the following. So I will start off by recapping what we can do about these questions if we know the model. Right? In a model-based scenario, what can we do? Can we answer this question? Right, and for this, I will use a tool called auxiliary functions and Lie derivatives. There's some fancy names for reasonably basic objects that you probably will have seen before. And then, having revised what we can do in the model-based settings, I will go into the data-driven setting. So, can we translate these techniques to data? And the answer is, well, to some extent, yes, using something called the Koopman operator and a technique called extended dynamic mode decomposition, which I will define. And then at the end of the talk, I will give examples of how this technology works in practice. Right, so let's jump straight in. I'm talking about dynamics, and we've seen, I've already shown an ODE, and ODEs are the type of model that I will assume for this talk. Right, so we have an ODE, x dot, dot means time derivative, so d by dt, equals f of t and x. X is normally a vector in Rn, t is time, and f is a vector maps time and the state of your dynamical system x to like a velocity, so it's a vector field. Initial condition is fixed, and I will assume that trajectories remain in some nice set capital X for all time, so they don't blow off to infinity, right? I'm not interested in modeling bombs that explode. I want to model things that remain nice and bounded. So the assumptions for these is that trajectories exist for all times, and they eventually enter some absorbing set, which is this capital X, and remain there for all time. So I can localize my dynamics in space. Most of the things that I will talk about actually are more general than this. You can apply to discrete time dynamics. So if you have a dynamical system that evolves in steps, you can apply to stochastic differential equation, to stochastic maps. In fact, a whole broad class of Markov processes. But I will not go into the generalization. I think it's easier to keep it simple. And so for this talk, this is the model that you should keep in mind, with the understanding that maybe we can do something a bit more general. Right, so this is the model. So what can we do? The tool that I will use to study this model are what I call these auxiliary functions and their Lie derivatives. And as I said, I have a fancy name for basic objects. So an auxiliary function is some continuously differentiable function, which I will denote by v, which takes the time and the state vector as inputs, right? So time runs in R and the state lives in the set X where the dynamics evolve. As simple as that, right? What's the Lie derivative? Well, the Lie derivative is this expression that you see here, where you take the partial derivative with respect to time, and you add f, which is the model for your dynamics, inner product, so dot, the gradient of v with respect to the x variable, right? So this looks like a chain rule, and that's exactly what it is. And I will denote this expression by L of v. Right? This is a function of time and the state of the system. Well, why is this of interest? I kind of already gave it away. It looks like a chain rule, and indeed it is. So if you evaluate this function LV, this lead derivative, at time t and along a solution of the differential equation, well, this is nothing other than the time derivative along the solution or the trajectory of the dynamical system. And so you can already see that if I somehow say something about this lead derivative as a function, then using this identity here in the box, then I can expect to be able to say something about the dynamics, right? And so this is not a new idea. It's actually quite old. And it goes back more than 100 years, at least, to the work of Lyapunov. So you can use this lead derivative to study auxiliary functions to study stability, and they go under the more common name of Lyapunov functions. So if you've done any control theory, you've seen Lyapunov functions, probably. If not, I will briefly explain. So suppose that you have an equilibrium state, which I will assume to be modeled by the 0 point. I can just choose the origin to be my equilibrium. Think of the drone that is hovering. That's your 0 state. You can prove that no matter how you perturb it, your dynamical systems will go back to that state if you can find a Lyapunov function, in this case v of x, which is only dependent on the state, not on time, that satisfies a bunch of conditions. So it should vanish at the equilibrium. It should be positive elsewhere. It should blow up at infinity. That's the last condition. And then crucially, the lead derivative should be negative at every point other than 0. And so the reason why this works, just intuitively, is that this V acts a little bit like an energy. And this condition here on the lead derivative tells you that as the system evolves, energy decreases. So energy decreases up to the equilibrium. So I will illustrate this with a video here on the right. It's a two-dimensional dynamical system. So there's two states, x1 and x2. And there's an equilibrium point here at the origin. And the level sets that you see, the contours here, are level sets of a Lyapunov function. What you will see here is the value of this Lyapunov function as a function of time when I start my dynamics from an initial condition, which is the black point up there. And what you will see is that this point will zoom out, so it will originally go far away from the equilibrium, so it looks like it's unstable, but then eventually will turn back and it will go in. Right, so if I let the video play, you will see exactly that. So it looks like you're going away, but actually you turn around. And if you look, in fact, at the value of this V, it's monotonically decaying. So that's the intuition for why these functions work. Right? So if I can find a function V that satisfies these conditions, which have nothing to do with the dynamics, right? I just need to check inequalities at points. I don't have to simulate dynamics. Then I can make a statement about stability, which is a dynamical statement. Question?
So in this definition, there is no dependence time
Correct.
for the but in the previous slide when we defined the derivatives, you did. So
Yes.
Are you interested in the general case or you also have?
We are interested in the general case because, thank you for the question, because stability is one particular dynamical question, and it turns out that you can get away with something that is time independent. But there are many other questions. For instance, if you want to make predictions after, I don't know, one time step or one time unit, then you can answer this question using auxiliary functions that depend explicitly on time. In this talk, the questions that I pose can be answered using auxiliary functions that are time independent, but in general, that's not the case. So I'm just keeping things simple, but yes. Okay, so this is stability. That was the first question. What about average behavior? Well, here I need to do a little bit of math to convince you of why this thing works. So let me start with some notation. I will take some function z of the state of my dynamical system. I call this an observable, and I want to compute the average of that. So that in the original example was the vertical coordinate. So that would just be the vertical coordinate of the point. So how do I define the time average? Well, I integrate between 0 and time t, divide by the length of the time window, and I let the time window go to infinity. Now, of course, this value might depend on the initial point, x0. Right? So in general, you change the initial condition, your system will do something different, so the average value that you get out could be different. It will depend on the initial condition. So I would like to estimate or ideally compute this value, but perhaps maybe estimate it. So where do auxiliary functions come in? Well, it turns out that if you take the infinite time average of the Lie derivative of an auxiliary function that depends only on time, for any initial point, you jump to the right, you get 0. And the reason is that really, if you plug in the definition, you're just integrating a time derivative. But then I can integrate, and I get a numerator that remains bounded because v is continuously differentiable and my trajectory is remaining a nice bounded set. That's kind of the assumption. So the numerator remains bounded as time goes to infinity, the denominator goes to infinity, outcome 0, right? So using this, it's kind of almost immediate to see the following result, that I can estimate from above the infinite time average of my observable for a certain initial condition, if the bound beta satisfies this kind of inequality here for some auxiliary function L, which again does not depend on time. Well, why? Well, if you take this inequality here and you just average over time, the inequality remains true, but then the average of the auxiliary of the Lie derivative vanishes, and you are left with exactly the inequality that you want, just rearranged. Now, of course, it makes sense to ask, what is the best bound that you can prove, right? Choose the Lie derivative, choose the auxiliary function v such that the Lie derivative satisfies this inequality and such that the beta is as small as possible. So really, I want to solve a minimization problem for this upper bound. On the other hand, the result is true for all initial conditions, right? And the right-hand side knows nothing about the initial conditions. So this bound actually applies to the maximum time average. So it gives me an estimate for the largest possible time average that I can see over my dynamics if I change the initial condition of my system. And now, if you know a little bit about optimization, you see a soup and an inequality with an inf, and this kind of smells like duality theory. And this looks like a weak duality argument. And for those of you who know a little bit of optimization, you might ask, are they strongly dual? Is that really an equality between those two? And it turns out in certain cases, yes. In fact, often in practice, you see equality, but you can actually prove that if your dynamical systems remain in a nice compact set, then the maximum time average is exactly equal to the smallest lower bound using these auxiliary functions. Right? So this is kind of not as standard as the diagonal theory for stability, but it's a pretty nice characterization. And I would like to point out that the maximization over trajectories, over initial condition here is normally a non-linear, non-convex hard problem. But the problem here on the right is a linear problem because the constant beta and the function v appear linearly in this constraint, and L is a linear operator. So the problem on the right is infinite dimensional because I have a function v, but it's linear. So in some sense, it's easy to solve. Okay, so we could go further, in fact, and if you remember, I said there was a third question that I cared about, which is how do we find these periodic orbits that form a skeleton of chaos? Well, it turns out that very often, time averages are optimized by periodic orbits. So for that Rossler attractor, there was this periodic orbit that went around once before coming back to its initial point. And let me just claim for now and hopefully convince you later that this orbit actually maximizes the time average of the vertical position. Now, if I didn't know it, how could I find it? Well, it turns out that you take the auxiliary function that gives you the upper bound, and if I have an upper bound which is good, then I look at the set of points where this expression here, beta minus the observable that I care about minus the Lie derivative, is sufficiently small. And there is theory that tells you that the optimal orbit should lie inside this set for a long fraction of time. And in fact, if I take that set and I plot it, you get this red set, which you see captures the shape of the orbit and the location in space pretty accurately. Okay, you're missing a part here because maybe the point goes very fast in this region, so it doesn't spend a lot of time here. And it looks like the orbit is outside the set in this part here on the left of the plot, but that's because this region is so thin that the thickness of the line that I'm plotting is thicker than the thickness of the set, so it looks like it's outside, but actually it's inside. So if you didn't know the orbit, you could use this as an initial guess for where to look for it. That's the point. And that's how you can use auxiliary function to somehow pull out periodic limits. And I will try to do this at the end of the talk in a slightly different setting. Okay. So takeaway message from this first part of the talk is that this auxiliary function and their Lie derivatives are pretty powerful tools to analyze nonlinear systems and do dynamical system analysis. Right? And in fact, you can ask a lot more questions. What about finite time predictions? What about predicting reachable sets or Bayesians of attractions of equilibria, or all sorts of things? There's a whole industry of techniques that are based on auxiliary function to answer that kind of question. However, right, you should be complaining because I always said, if I can find an auxiliary function that satisfies certain inequalities, then I can make a statement, right? Well, how do I check? How do I look for these things? It's not immediately obvious, right? If you've taken a class in control theory and you studied the apple of stability, you will remember that your teacher will have told you the apple of theory is very powerful. However, it's almost impossible to find these things in practice. It's very hard. You need a lot of intuition. So how can I look for these things? Moreover, this Lie derivative is an expression that looks like this in the general case where you have time dependence. And in here, there's a model for the dynamics. What happens if I don't have this model? How do I get access to Lie derivatives, right? What do I do? So in the next few minutes, I hope to answer the following two questions and maybe show you a couple of examples. Starting with the first one. So how do we check these constraints? So here is where the polynomial optimization part of the talk comes in. Yes, that's a question.
So, what do you mean by you have access to the model? You mean like in a data-driven sense?
Correct. So suppose that I can observe some dynamics, but I don't know what the equations of motions are. But I can measure data. Does this mean that all of this technology using auxiliary function goes out of the window because I can't build the Lie derivative? Or maybe there's a way of building the Lie derivative from data, and that's where we're going.
But this is a question and also a guess, right? But you can compute derivatives from the data, right?
You can. So that's exactly what I will show you, and the point will be to show you that you can recover or approximate these Lie derivatives, even if you don't know the expression from the model, just from measurements of your system.
Okay.
So I will go back to that. But for now, let's assume that we know the model, that I can compute the Lie derivative explicitly, but I want to optimize, right? So how do I find these objects? So I want to do this in the context of these time averages because I only have one condition involving the Lie derivative and maybe some bound on the time average of the observable G, right? So let's look at what we have. Well, the Lie derivative, now I have an expression because I have the model, so I can calculate it, and so I can plug it in. And now what do we have? Well, I have G and F, which are somehow data. Right? G is the observable that I care about, and F is the model. They are fixed functions. Let me assume for the time being that they are polynomials. Why? Because I like polynomials. They are nice. They are somehow, they feel like they're computationally tractable. So it's a simple setting. If I can't handle polynomials, then probably I can't handle anything else, right? Then what else do we have? Well, we have the constant beta, which is a real number. That's easy to handle with a computer in an optimization routine. And then we have V, right? V is up to us. I can choose whatever I like. So why not choose it to be a polynomial, right? And I will tweak the coefficient of this polynomial, or I will at least try to tweak the coefficients of this polynomial such that this inequality holds, right? And then when you look at it, everything here is a polynomial function. So the left-hand side is a big polynomial expression with coefficients that you can tweak. And you want to ensure that this polynomial function is non-negative. Now, it turns out that this question is NP hard in general, so it's very hard to solve. So the strategy is, forget about inequality. Let us try to prove that the left-hand side is non-negative by representing it as a sum of squares of other polynomials. Now, if I can do that, squares are non-negative, clearly. Sums of squares are non-negative, so this is a sufficient condition for my inequality. In general, it's stronger than non-negativity. Not every non-negative polynomial can be expressed as a sum of squares like this. But this is convenient because it turns out that looking for the sums of squares representation is equivalent to looking for a quadratic form representation when you take all monomials of your variables up to a certain degree, you put a big vector, and then you pre and post multiply with this vector a big matrix, which needs to be positive semi-definite. So it turns out that if you can find this sort of matrix representation for your polynomial, then you can also write it as a sum of squares. And now it looks like the problem is tractable because all I need to do is find this matrix. And finding positive semi-definite matrix, is a problem that is computationally tractable. It's called a semi-definite program. And there are algorithms that are established that can do this for problems up to a certain size. So you just download the solver from the internet and you run the computation. Now I could give a whole talk about doing this. In fact, there's university courses about this. So I won't do that, but I will show you an example of what's possible. So I want to go back to this Rosler attractor, which I started with, and I want to, my original motivation was finding the mean vertical position. So let's try to put these bounds on the vertical position, so the average of the x3 coordinate. And I will remind you that the bounds apply to every trajectory. So this is the chaotic trajectory, but in here there are also the periodic ones, like the short one, but maybe one of period 2 that goes around twice, one that goes around 3 times, maybe another one, and so on. So the answer that I find has to be valid, a valid estimate for all of these trajectories. So what happens if I implement the method and run these polynomial optimization techniques in a model-based way? Well, on the left here, you see the degree of my auxiliary function, which is a polynomial. And you could imagine that the more complicated it is, so the higher the degree, the better I can do. And that's exactly what you see. On the right, you see the values of the optimal beta, these upper bounds. And you see that they start from something very high, so 30, but then very quickly they sort of come down and they seem to be converged to something like 1.3 or 5. And this is exactly what the theory predicts. In fact, if you take this number and you compare it to the value that you get for the shortest orbit, you see an incredibly good agreement. Right? So this is exactly what the strong duality theorem that I mentioned at the beginning tells you. These computations, these upper bounds converge. So now, this is why I claimed at the beginning that this shortest orbit was the one that optimized the average of the vertical coordinate. It's because I have these computations, right? And that's very good agreement. In fact, maybe you remember I plotted also some localizing set if I didn't know what the orbit was. Well, this set was computed using this polynomial auxiliary function of degree 21. So that's how I computed that localizing set. Question.
What was the red thing?
So the red thing is a set where, I have to go back a little bit, where this quantity here is not just non-negative, but also small. Yes, so you take the optimal V and the optimal beta that you find, you plug it in, and then you look for points where this quantity is small, you get the red set. Yes?
Why degree 21? Was it like good enough, or was it like a decision of computation time?
It looks like it's good enough. It's not too slow. I could have pushed it a little bit more, but it looks like it's reasonably well converged already. Sorry, I just decided to stop there. So there was one there, and then
So for degree 21, how many variables has the degree function?
Oh, good question. I can't tell you offhand, but I think we can find out.
Yeah, it was more or less the same. It's when you say degree 21 are all monomials of mixing variables up to 21.
So in fact, it turns out that so V is degree 21. So let's do a quick count. I need to go back to the expression. So I have to compute this guy and see what degree this guy has. So this is degree 21. The gradient has degree 20 because I differentiate a polynomial, I lose a degree. But then I multiply by the dynamics, and the Rosler attractor is quadratic. So 21 minus 1 plus 2 is 22. So that means that in this vector, I list all monomials in 3 variables up to degree 11. Because I have 11 times 11, 22. You double the degree. So how many are there? Well, 3 plus 11 choose 3. So 14 choose 3. I don't know what that. We can write it down and then we can figure it out. So I have, for that computation, matrices that are, this matrix here has size 14^3 by 14^3. Symmetric, so you have the size, but that's what it is. Okay, any more questions? Okay, if not, then let's keep going. So hopefully that convinced you that we can cite these constraints computationally, and if I know the model, I can actually do pretty well. Now, what if I don't know the model? What should I do? And as I mentioned at the beginning, the tool is to use this Koopman operator. And what it is just a linear operator that does the following. You give me a function v, an auxiliary function v, and I come up with a different function, which I will denote by k tau v, which predicts the value that v would have at time step tau in the future. So you evaluate k tau at this point, k tau v at this point, and that's the same as evaluating v if you move the point along the trajectory by a time step tau. That's what this does. So it's kind of predicting the future. Right? Why is this useful? Well, two reasons. The first one is that if you remember the lead derivative evaluated along trajectory is somehow a time derivative. Well, but this, if you plug in the definition, that's the same, well, take v at the next after a little time, subtract v at the current time, divide by the time step. You do a sort of definition of derivative, and then you let the tau go to 0, right? So more formally, the lead derivative operator is the generator of the Koopman operator. So there's this relation between the two, right? So if I can somehow approximate the Koopman operator from data perhaps, well, then I automatically get an approximation of the lead derivative through, let's say, finite differences, right? So this is the first reason why the Koopman operator is interesting. And the second one is that indeed we can approximate it from data. Okay, so the strategy is to approximate the Koopman operator from data using a technique called extended dynamic mode decomposition, which is reasonably well known. And then from that, you deduce approximation of the lead derivative from data, and then you use this approximation to optimize the auxiliary functions, and therefore try to make statements about the dynamical system. So how do we do the data-driven approximation? That's the key ingredient here. As I mentioned, is something called extended dynamic mode decomposition, or in short, EDMD. And the idea is the following. You take your auxiliary function v, and you try and expand it using some dictionary or basis function phi. I call this an expansion dictionary because that's what I want to use to expand my v. Now I want to approximate the Koopman operator applied to v. Well, because the Koopman operator is linear, I can bring it inside and apply to the basis function. So all I need to do is I want to approximate the Koopman operator applied to the basis function in the expansion dictionary, and I will do this as linear combination of some approximation dictionary. Usually in the literature, these two dictionaries are the same, but you don't have to. In fact, it pays to take them to be different. Right? So you have an expansion dictionary and an approximation dictionary. How do you find this approximation? Well, this is where the data comes in. So the data will be in terms of times, t, ti, current state xi, and then measurements yi of the state after a time step tau. So a data point is your current time, your current position, and where you land after a time step tau. And if you do that, if you have this data, all you need to do to find out these Kij coefficients in the approximation is solve a least squares problem where you evaluate your expansion dictionary at the next time step. That's like evaluating the Koopman operator applied to these functions, which is what I want to approximate. And I measure the error that I have from my approximation. That's all. And then you solve this least squares problem. There's an analytical solution for that. It has to do with pseudo inverses. So you can calculate the optimal K matrix here just by doing a similar value decomposition. So this is really easy to solve. Questions?
Is there a justification for like the size of n you need to pick here? Or
N is the number of data points. I will mention a theorem in a second, which shows convergence as n goes to infinity. There are actually estimates for how much data you need for a certain approximation error. They're quite decent. I will not comment on those, but we can talk about it offline.
How do you choose the dictionaries?
The dictionary is up to you, right? So
Yeah,
in general, the more the better.
I mean,
Like,
what's the-
normally, I like
What's the idea?
The idea is, well, for me, I want to use polynomial optimization. So I would like V to be a polynomial, but that tells me that the dictionary should be a polynomial. And I also want the Lie derivative to be a polynomial. And that means that I would like this approximation here to be a polynomial. So I will use polynomial dictionary. Yes.
Related to that, I mean, you said in the previous slide that you can approximate Lie derivatives by finite differences, but I think once you're in the polynomial setting, you don't even have to, right? Because you can, like, this Koopman operator is linear, so you can kind of validate its derivative. You don't need to take finite differences.
If I know the model.
No. You estimate the model, you get some linear operator, and I'm saying.
Very good question. I'll come back to this question. So there is a question of why not fit a model to the data and then calculate the Lie derivative exactly? Well, there's a good reason for that, and it has to do with my last example. So I'll come back to that. Please remind me if I forget. Okay, so now this is a recipe to approximate the Koopman operator from data, and we basically replace this k tau of V with effectively the multiplication of a matrix, right? So once I have this, I take my auxiliary function V expressed in this expansion dictionary, and instead of going down the model-based route where I would want to take this limit where I have this Koopman operator, I go down the data-driven way, I figure out what the K matrix is, and I just take this finite difference approximation, right? And you might expect that if you do things right, these two things are approximately equal to each other. And the quality of approximation, of course, depends on a number of things. As you already pointed out, it depends on the number of data points that you use. The more, the merrier, right? It depends on what dictionaries you choose. And in particular, if you think of this dictionary being fixed, it will depend on what dictionary for the approximation you choose and how big that is. And then, of course, because there's a finite difference involved, there's a tau parameter. This approximation, finite difference approximation, will, the accuracy will depend on how big or small that tau is, the sampling data. Okay, so can we show that somehow there is some convergence? And the answer is yes, right? So we have in the paper some rigorous convergence analysis, which I do not want to go into too much detail, but I will summarize as follows. So the main theorem is that you view the data as being a realization of some random variable with some distribution mu, and you assume, which is what you often see in practice and what you can also show under certain conditions, that if you do sample averages, they will converge to expectations against the distribution. Well, in that case, almost surely as you generate the data for almost every sequence of data that you generate, this approximate derivative converges to the exact one in some L2 sense that has to do with this probability measure in a triple limit. Infinite data, n goes to infinity, infinite sampling rate, so tau goes to 0, and infinite dictionary, provided that your dictionary has good approximation properties. For example, polynomials on compact sets. For example, finite element basis functions on for sublevel. Yes.
So in group, the limits have to be taken in order?
I'm about to comment on that. So the question is, does the order of the limit matter? And the answer is yes. What is important is that the infinite data comes first. So that needs to come first. The other two you can actually solve. I don't know, obviously this is suboptimal because in practice you always have finite data, but you can make the dictionary as large as you like. So you would like to swap these limits. Well, theory doesn't work like that. And in fact, you will also see this result in practice. As I mentioned before, there are people who worry about convergence rates. That's not something that I want to mention in this talk, but there is literature on that. So I can give you pointers if you're interested. Right, so with that, hopefully some elements of, yes, we can approximate Lie derivatives from data, even if we don't have the model. So now we have all of the ingredients. Can we do really in practice system analysis based on data? So for the last, how much time do I have? About 10, okay, then some examples. Right, so the first example comes from stability. And this is exactly the same example for which I showed you the little video of the diagonal function at the beginning. So two-dimensional dynamical system, in this case it's polynomial, because I like polynomials and because then I can compare data-driven analysis to model-based analysis. So I will take this dynamical system, it has an equilibrium at the origin, and I would like to prove that it is stable. How do I generate data? Well, I take the unit disk around the origin and I see trajectories at equispaced points. I think I've taken k trajectories, so you take k points, and then for each initial condition, you simulate for about 2,000 time steps with a time step of 0.001 10 to the minus 3. So that means that the number of data points is 2,000 times the number of initial conditions that I take. So that's how I generate the data. What about the dictionaries? So my expansion dictionary will be monomials of degree 6. That means that I'm looking for a Lyapunov function V, which is a polynomial of degree 6. For the Lie derivative, I will approximate using an approximation dictionary of degree 8. Okay, so why 6 and 8? Well, because I kind of know in this example that this system is cubic. So if I have a V Lyapunov function which is polynomial of degree 6, then the exact Lie derivative is a polynomial of degree 8. So in some sense, I'm a little bit cheating to begin with, but this is the simplest setting. If this fails, no hope, right? So what are the results? Let's see if the slide changes. Okay, so on the left, you see the exact Lyapunov function, one that I calculate using polynomial optimization with the exact Lie derivative. On the right, you see what I would guess using only one simulated trajectory with 2,000 data points and using the approximate Lie derivative. But if you compare the two pictures, you kind of guess that this is wrong. The one on the right doesn't really work, but the Lyapunov functions are not unique, right? So maybe I just found a different one. So what I can do is I can take the function on the right and I can plug it to verify into the conditions on the left, because for this example, I know the exact Lie derivative, right? So maybe I was lucky. Well, turns out that I wasn't, right? It was really wrong. However, if I start increasing the number of data points, the picture looks a lot better. Still not a true Lyapunov function, because it doesn't satisfy the exact conditions, but much better. And if you increase the number of data points, then eventually you get something that really satisfies the conditions of a Lyapunov function. And even if I increase the data more, then even better. Of course, this works for this dictionary. And I said that I cannot cheat it because I chose this dictionary to be the right one. So what if I didn't know? Well, you would say, these are good results. Increase the size of the dictionary, right? Until maybe you see convergence. So you can do that. So here is if you take a dictionary that is too big for this problem. So you go to monomials of degree 10, and the picture kind of remains the same, right? But then, maybe some of you are still not convinced, and you say, no, right? Please convince me that you really converge, increase even more. So I go to 12, and now I have a problem, right? Because the picture starts to look bad. But then I remember the theory, and the theory says, no, you're increasing the size of the dictionary whilst keeping the amount of data fixed. But the theory tells you that you converge if the data goes to infinity first. And indeed, if you start increasing the data, all of a sudden, you see that the picture looks good again. Right? So data going to infinity first is important. And you see this in calculations. Right. So that was stability. What about time averages? Well, I can go back to my favorite Rosler attractor. Again, I generate some data. I take some polynomials, or my auxiliary function now will be the percentage basis of some. And my approximating dictionary, in this case, I do cheat. I take the right degrees. Turns out to be D+1. That was the 20, 21, 22 calculation that we did earlier. And you see here in the table, the last column gives the exact upper bounds for small polynomial degrees. And the three columns that are colored in the middle give you the upper bounds that you would get from the data-driven analysis for 10 to the 4, 10 to the 5, and 10 to the 6 data points. And you see that for small polynomial degrees, the results are always very good. If you increase the polynomial degree, if you increase the size of the dictionary, then all of a sudden you need more data to get very good results. So if you compare these numbers in green to the exact ones, the accuracy is reasonably good, considering that it's a data-driven analysis. More interesting, rather than these numbers, is can I pull out the periodic orbits that forming the skeleton of this chaotic attractor? Right. Now I could take the optimal V and plot that localizing set, but that's going to be hard because I'm somehow trying to approximate some really complicated curves in space. That's not going to be very easy. Instead, I'm gonna take a different strategy. So here's the attractor. What I will do is I will realize that here is pretty flat. So let's cut it. And let's initialize a trajectory here, and I will run a simulation, and I will measure I am here, and I will let the simulation run, and I will record where I cross again, and again, and again, and again. So I can build a map that tells me if you are on this point, on this black line, you come back at this other point. And if all of a sudden you find a point that goes around and lands back where it was, then that's a periodic orbit, right? So instead of looking for a trajectory in space, I can just look at points on this line that come back to themselves under this iterated map. It's called a Poincare return map, and you can plot it. So it looks something like this. So the horizontal axis is your current position along that black line. And on the vertical axis, it tells you where you come back, right? So if you find a point that comes back to itself, and that means if you find a point on the diagonal, like this one, then that corresponds to a periodic orbit of the original attractor. Okay, so now I go from looking for loops in 3D space to looking for points, which seems to be much easier. What's the catch? Well, I can plot this map, but I have no idea what the expression for it is. There's no analytical formula, and even if it were, it will almost certainly not be a polynomial. Right? So here, in order to identify these periodic points, is really data-driven, because I can measure this map, this return map, but there's no formula for it. Okay, so this is the first orbit, but you can look at trajectories that go around twice before coming back to themselves, and then you can run exactly the same idea, but instead of plotting current position versus the next one, you plot current position versus position in 2 iterations, so n to n plus 2. And points along the diagonal here will correspond to orbits that go around twice. So there's one here, the red one, which corresponds to the orbit that I already know, just traverse it twice, right? But there are also 2 other ones, and these correspond to this orbit that circles around twice. Of course, you can do it for things that go around 3 times, 4 times, 5 times. But as you keep going higher, maybe you try to find something that goes around 8 times, then the picture looks like this, and it's kind of difficult to do that analysis, right? So instead, I propose to do the following. Let's consider the one-shot Poincare return map. And let me use this idea that time averages are optimized by periodic orbits. And so what I will do, I will generate random observables for this map. I will bound this infinite time average. Now it's a discrete time dynamic, but there's an extension of the theory to that. That's fine. I will have to use approximate Lie derivatives for that because I have no expression for this map, so I don't have a model. And once I have these bounds, I will try to extract the optimal trajectory, which in this case, because it's a map, it's a periodic point. So I only need to find a point instead of a loop, right? And here we come back to the question of why not just fit a model? Well, because if I fitted a model to this line, and then I start to iterate it with itself, errors will propagate. So finding, even for a model that I fit, finding orbits, if you fill in this picture, will not be very good because the model inaccuracies will propagate and will ruin your chance of really finding periodic orbits for the original map. So that's kind of, we found that this works a lot better to work directly with the Lie derivative. So you go directly for the approximation of the object you want, rather than an approximation of an object, which you then use to approximate something. And it turns out that this works. So these are orbits that we recovered with JSON for this example from this Poincare data. And we get all of the short ones, which we kind of already knew from these diagonal arguments on the plot. But also we easily find things that go around 8 times. I think this goes around 13 times. And things start going around like 17 times. So these are long orbits. And you kind of see that these are difficult to discover if you try and fit a model first because of inaccuracy propagation. And then hard to do from a model-based perspective if you look at the whole loop, because when I'm trying to approximate this line using some level set of some polynomial, it's going to be extremely hard. But the data-driven approach, where you cut the attractor and look at this Poincare data, works extremely. So I think that is all I have. In fact, we're kind of bang on time, I hope. So to summarize, these auxiliary functions and their derivatives are powerful methods for nonlinear system analysis. If you know the model, and hopefully, given these latest developments, also sometimes if you have data, right? So we have this data-driven approximation of the derivatives with guaranteed convergence, thanks to this connection to the Koopman operator and the work that people have done to approximate the Koopman operator from data. In this work with Jason, we extended the convergence theory to a more general setting. We weakened the assumption, but very similar results existed in the literature before. There are a couple of bottlenecks. The size of the data sets. I used a lot of data points for systems which are kind of low dimensional, but this is somehow not unexpected if you look at the theory. The theory tells you data to infinity first, and in fact, if you look at the estimates for how much data you need, then it turns out that the estimates are not that great. So you do need data, but that's okay. There are situations where you can generate data and still answer interesting questions like finding periodic orbits. There is another bottleneck, which is the cost of the polynomial optimization. I had to find that big positive semi-definite matrix. And you already asked how big is that matrix? Well, big, right? Because the size grows combinatorially. Unless you are very clever about what you do and you know symmetries of your system. But in general, there's a bottleneck there, right? So there is these two bottlenecks. However, I would say there's excellent results for reasonably low dimensional systems. Also for questions which are hard. I think the periodic orbit example is a very good one because that is a question that is hard to answer in general, and we have very, very good success, despite the fact that you need maybe a lot of data and maybe the polynomial optimization has bottlenecks. So with that, I will stop. Thank you for your attention. If you are interested, well, I'm here for another couple of days. I understand it's a holiday, but this afternoon I'm here, so please come talk to me. And there's a couple of links to the papers if you are interested in knowing more about reading about it. Thanks.
We have time for questions.
So you mentioned that you need to have data that's proportional to the degree of the polynomial. So because it's a bit misleading because the degree of the polynomial doesn't tell you how many terms you have on your basis. So if I have, or what would be, or do I need a constant factor of the number of elements in my basis in terms of data, like 3 times the dimension of your
Good question. We will have to look at these references that have precise estimates. We can look at that. We can look at that offline. I can't remember there's a complicated expression. What seems to be the case is that normally, so the rule of thumb is a square, the square root of the number of data points. But of course, there are constants in there, which might depend on how big the dictionaries are. That I don't know. Yes.
So in the last examples, you used this Rössler.
Yes, those are
What's called so where the dynamics, a priori the dynamics is polynomial, right?
Correct.
Have you checked a system where the f is not polynomial?
Yes. Yeah. So we have done, in fact, Jason has done a similar calculation for another 3-dimensional system, which is called the Thomas system, which has sine and cosines, non-linearities. So it seems to work. And of course, in this Poincaré map example, I don't know what this map is. I mean, it kind of looks like it could be fit well by a polynomial, but there's no reason to believe that it should be. And I honestly have no idea what the function for this map is. Because I can simulate it, but I have to solve a nonlinear ODE for a certain time, which I start from this line and I have to simulate until I hit the line again. I don't even know how long it will take to hit the lines. So it does work if you have maps that are non-polynomial, but perhaps they are reasonably well approximated. So in this case, I think the calculation that we did was kind of behind the scenes, assuming that a polynomial of degree 4 would be a reasonably good approximation to this one, which if you look at the shape, you cannot believe, but it's like an x squared, but a little bit more little bit straighter.
It's too straight, so
Yeah.
I figure.
Well, it's not purely x4, like the x plus constant plus x squared plus x to the 3 plus x to the 4, you do the coefficients, you cannot reproduce the shape. So yes.
To get this shape, you kind of cut it, like knowing the shape of the system and like tuned to this system. How
Correct.
would you like generalize this kind this approach when the system can be much more complicated and you just can't put a line?
So normally you don't cut with a line. This is a very special situation because the point is, let me just pull up the picture again. So here it looks like this part is flat, so I cut it with a line. Actually, it turns out that it's an approximation because this part of the attractor is very, very thin, but it's not actually flat. So normally what you would do is you would cut with a plane. You introduce a section, it's called a Poincaré section in space, which normally is a 2-dimension one surface. So if you are in 3D, normally you cut with a plane, 2-dimensional plane. If you're in n dimension, you cut with a plane of dimension n-1. So you go from continuous dynamics in n dimension to discrete dynamics, this return map, in n-1 dimension. This is a special case because we get a very good approximation with a 1-dimensional cut. But actually, if you look at the data, it's not exactly 1 dimension. And then where you put it, well, then you need to know roughly what your system is doing. So normally you choose the section for the system that you want to study. So why do I put it here and I don't put it here? Well, I could have put it here, right? If I want.
You do examples with non-uniform time step?
No, we didn't. We didn't do an example with a uniform time step. And the reason is that the approximation of the Koopman operator, let me put up the picture for that. The reason is that I'm approximating this guy, and this guy depends on the choice of tau that you choose. So you have one operator for a certain time step. If the time step varies, then you're approximating different operators. So I don't know if you are, maybe you can approximate in some sense an average of that, but that we haven't tried. I don't even know what the theory will look like.
I agree, right? That also depends on the derivative of the in that section, right? So could be that it is order delta t or the tau, right?
Absolutely right.
But
Yes.
also depends on the derivative.
Yeah, absolutely right. So one would have to do a more calculator analysis, which we haven't done, which is the asymptotic convergence. The next step would be to do the quantitative analysis. I think Jason is looking into that direction. He has some results, but he will be the person. Found many answers.
What happens, because typically you have observations about the system, but they are corrupted by a little bit of noise. And in that case, how much does this change? Like how robust it is?
Very good. So there are ways of handling this. You could potentially, instead of trying to do derivatives, you can write an integral version which smoothes somehow the errors. It's like doing, you control when you have noisy measurements, you don't want to differentiate, you want to integrate because they are smoothing things. So you could try to build approximations that somehow fit an integral expression. In general, actually, it turns out that if you see the noise of your measurements as being part of your dynamics, then and so you view your state as being somehow noisy, then the method learns the right expression for the Lie derivative automatically. So you don't have to specify whether your system is in fact something that is quite cool about the method, which I haven't mentioned. The expression for the Lie derivative, if you have the model, will look different if you have a discrete time system, a stochastic system, a deterministic system, and so on. But if you apply the method, it doesn't matter if it's deterministic or stochastic, you will get exactly the approximation to the right object. So if noise is part of your dynamics, then you automatically learn the right expression where you view your system as being stochastic or deterministic, not monetary.
Your time?
Yeah, sure.
So you mentioned at the end that when solving these optimization problems, there's a lot of symmetry that can be exploited sometimes. It's not clear to me at all where symmetries appear in this context. So maybe can you?
Okay, so symmetries will arrive in the model-based version because okay, maybe let's look at this expression here. So suppose that I have a model, and suppose that I know that I don't know that the model is equivariant if I apply a transformation to x. I don't know, it changes x to minus x, then f goes to minus f. Well, then it turns out that there is theory that tells that without loss of generality, often you can take v to have the same symmetry. And then the whole expression for the lead derivative has a symmetry. And that allows you to reduce the big monomial basis that you have to list. And that big matrix, you can do symmetry reduction when instead of finding that big positive semi-definite matrix, you can plot diagonalize. So that's where it arises. That is in the model-based case. Of course, if you know that your system has symmetry, you can build in the symmetries in the data-driven discovery. But of course, in general, you just measure data and discovering symmetries from data, maybe you can, maybe you can't. I don't know how to do that.
Okay, but that's the kind of symmetry
That is the kind of symmetry that I'm thinking of. Yes, the model has some, x to minus x type of symmetry. You can have more general symmetry group actions, and you can use techniques from algebra to then apply symmetry reduction to your semi-definite problem. That's how symmetry is inherited from the original dynamical system.
Sure question. This is more open, so I'm not familiar with this, but so in the system that you showed, typically they're polynomial, but they're a very sparse polynomial. They don't have like terms of any products of variables. So my question is that a structure that can be exploited when you try to find this function, or does the Lyapunov function inherit sort of sparsity?
In general, no. There are very, very special structures that are cascaded systems. So for instance, things that look like cherries. So if you have couplings between x1, x2, and x3, and then x4 and x5, right? So this sort of structure, if you have x1 influencing x2 and therefore indirectly x3, and then x4 and x5, but x2 and x4 do not talk to each other, well then you can look for a V that is somehow the structure is this branch plus this branch. But in general, you have to couple it. So that's a little bit annoying, but of course you can try, but in general, you find that you have to couple it. Good question.
Okay, let's give a final class.